Hi everyone. Thank you for coming out to lecture 4. Today we have Zach and Jonas talking about transactions, and we'll have a few live demos too. So that's the first for these lectures. So yeah, we'll get started. Thank you for coming out.
Cool. Hopefully everyone can hear me okay. So today we're going to be talking about transactions. We're going to mainly be using Ethereum as a case study. If you guys haven't heard of Ethereum, it's just about the second largest household name out there. Yeah, so that's why we're going to be using it today. Cool. So the main objective for today, we're going to be mainly focusing on connecting kind of some of these past course concepts and then looking at it through the lens of transactions. So we're going to be looking at consensus and cryptography concepts and look at it through the lens of transactions and how it interacts with the blockchain organization. Another goal for today is to gain kind of a broader technical understanding of how a blockchain might work. And yeah, so we'll be going through some summaries of past courses as well. So hopefully that'll be helpful for you guys. So some important questions for today. So why is requiring transaction fees important? So if you guys have ever interacted with some of these blockchains, you'll notice that there are transaction fees often. So one reason for this is because there are people with malintent who would want to spam transactions or even cause infinite loops. So by implementing transaction fees, we can kind of make that more difficult for them to do. In some blockchains, these transaction fees even go to going back to the miners, keeping the miners profitable and allowing that blockchain to continue to run. When we're talking about the transaction nonce, we want to think about why it's important. Specifically for our purposes, it serves as an identification as well as allowing us to replace signatures for each transaction. So it distinguishes and differentiates transactions and allows us to, make sure we can tell individual transactions apart. Some other important questions that we'll look at answering are: how do transactions reliably alter critical blockchain data? And why is it important to prove that a transaction is executed, which again, we'll look at later. The outline for today, we're going to be looking at summaries of past courses. So when we talk about those during today's lecture, hopefully you guys can still understand what we're talking about. We're going to be looking at nodes and their role in blockchain. We're going to be looking at transactions and their life cycle. We're also going to be going through some live demos, actually interacting with a node. So that'll be cool. And then we're going to be going over the structure of a transaction and the structure of a block.
Let's just briefly summarize what we've gone over so far. So in the first lecture, we were mostly talking about why blockchain matters. And I found this tweet talking about like a French bank who put the euro on the blockchain. And in the code,
Cool.
In the code for this digital version of the euro, there's actually a functionality where the authority can take all your money. And this just goes to show maybe some of the centralization risks that are associated with traditional fiat currencies. This is completely unacceptable in the blockchain world. Most of our cryptocurrencies are very well audited. And if this kind of functionality appeared in a cryptocurrency, it would be there would be a huge issue. So we had Jay Freeman come talk to us a little bit about consensus. And one of his main points was that consensus was a classic CS problem that blockchain projects avoid, right? Avoid solving. And maybe some of you are wondering why he said this. And basically the reason why is most blockchain networks do not actually come to a full consensus on the next state of the blockchain. We just kind of maintain our own version by ourselves, like all the nodes maintain a version of the blockchain by themselves. And then if enough people basically agree, then we just kind of roll with it. And pertaining to blockchain, some of the key things that consensus researchers are concerned about are which transactions are included. So what data do we include in the blockchain at all? What is the order of the transactions? And how difficult is it to go back in time and change past transactions? Jesus and Mateo also presented a little bit about cryptography. And so there's this idea of a public and private key pair or secret and public key pair, where the private key is just some random number. And we can derive the public key directly from the private key. And the private key is used to authorize transactions, which we'll see later. There's also hash functions, kind of similar to regular math functions, where you take an input and you feed it into this hash function, and you can get an output. And the key thing with hash functions is that given any output, it is very difficult to find the input, right? And hash functions are used pretty much everywhere in many blockchain implementations. Digital signatures, right, which are generated through the private key, and they authorize a transaction. And this authorization is undeniable and cannot be tampered with. So the main idea of a blockchain transaction is that it is a request to make a change to the current state of the blockchain. So that's actually very important. And I bolded this and underlined it and highlighted it because if you get nothing else out of today, maybe you can look back to this. Zach will talk a little bit about nodes.
Cool. So in order for us to understand nodes, let's first understand how they're implemented. So this is kind of through a distributed network. So maybe some of you guys have heard that term before, but it's kind of how a lot of these blockchain systems are distributed. And so this is kind of a map of these computers, and you'll see that it's actually worldwide. So to look at this in a different sense, there's this peer-to-peer network where there's not really one central system where this information is just being spread and distributed across all the different entities. So what are nodes? Nodes are downloadable software. So what is this software? It's the rules of the blockchain protocol. And you might think, what are these rules? Where do we find these rules? So it's from two main entities. So the first is the developers, and then any iterations to that is based off of community discussion. And the kind of the process for that is this community discussion occurs, and then eventually a formal specification will be actually written down. And then it varies from blockchain to blockchain how this formal specification actually gets implemented. But if the community decides to actually implement it, then it will go through that process. But the main point here is that there's a discussion and then a formal specification written down before any kind of implementation. One example of this is an Ethereum improvement proposal, which is exactly what we just talked about, where it's an actually formal written down proposal for updating the software that we see on these nodes. So again, nodes are just downloadable software, and that's what helps run the blockchain ecosystem. What are their main functions? So the key main functions are validating and updating the database. This is when we're talking about our ledger. So the nodes are actually what update our ledger and keep that up to date. They also are the entity that achieves agreement on the next state of the blockchain. So this is this concept of consensus that we've talked about a couple times now. Two of the large consensus protocols are proof of work, which is what Bitcoin runs on, and then proof of stake, which is what Ethereum currently uses. Nodes also serve as a connection point to the network for blockchain reading and writing. So we can actually use these nodes to get information from the blockchain. And we'll see this in some live demos later, but we'll actually be able to read what the current block number is and some information from any block. And so when we talk about this, this ledger that we keep updating and validating, this is where we can actually access that and check past transactions. So nodes can be written in almost all high-level general purpose programming languages. So what this actually means is that it's non-discriminatory. So anyone with a high enough level of programming is able to write to these nodes. And basically what this is stopping is any node from being in this hyper-specific language that only a couple people know. It would be very centralized. So when these nodes are able to be written in all these different programming languages, it almost decentralizes it because we have a variety of people who are able to write. So running our own node, this basically serves as a system to directly, trustlessly, and privately contribute to the network while increasing the network's decentralization. So we had this idea of don't trust, verify. And basically, by running our own node, we're able to just participate in this network. This concept of anyone can run a node is referring to the fact that you just need the hardware and then the software, and you're able to do it. There aren't really any more barriers to entry other than kind of a technical knowledge of how it works. So now we're really going to get into transactions, which is the main topic for today. So fundamentally, as Jonas said, transactions are merely just a request to make a change to the current state of the blockchain. So if we're in this current state T, some transaction occurs, we then find ourselves in this new state T plus 1. One of the core reasons why we say request to make a change is because we can't just allow people to make changes to the blockchain. Otherwise, we lose this whole concept of security. When we say request, it's so that these transactions can go through a verification process, and then that will be added. So this is a diagram showing some key differences between Web 2 and Web 3. In Web 2, you had to own a mobile device, you had to know a secret PIN or code, or through some biometric, that was your key, right? You either knew a password or you had your Face ID or a fingerprint. In Web 3 and blockchain, like this cryptography concept that we talked about, you have this private key, and that will actually help you sign and seal your transaction and make it so anyone can verify that that message came from the owner of this private key. There's a couple of vulnerabilities on both sides of this, right? If someone learns your password, they could get access to your system. In the same way, if someone were to gain access to your private key, that would also be very dangerous in the state of blockchain. So it's something to consider and, kind of analyze the pros and cons of both. So this is one of the key slides today. It's talking about the transaction lifecycle. So we're going to go through this pretty slowly. So the beginning of the transaction lifecycle is building the transaction. So fundamentally, this is what the transaction is, who it's going to, who it's from, what's being sent, how much is being sent. It's all the core data for the transaction. Once we have that, the signing of the transaction occurs. And again, that's through the owner of the private key uses their private key to sign this transaction. Once that occurs, this signed transaction gets broadcasted out to this decentralized network of nodes that we've been talking about, where it will then be verified. So again, this signed transaction goes out to this network of nodes where it'll be verified. Once the verification of this signature occurs, we see a transfer or transition from this mempool of data to a future block. So what do I mean by mempool? Basically, we see a transition from just this unconfirmed transaction in the decentralized network in a pool of unconfirmed transactions. And once it's verified, it moves from that mempool to a spot where a future block will occur. From there, it applies a change to the new state. So we're in this new state, and it's posting the new state in this new block. So basically, it goes from an unconfirmed transaction into a spot where a block will occur, and then we see the new state, and it gets posted and posted into this new state. From there, this new block is broadcasted and confirmed. So that's confirming the new block's validity. And once that block gets confirmed, the transaction, which is a part of that block, is now thereby also confirmed as being executed correctly. From there, we reach this concept called finality. This is when transactions are in blocks that are relatively old. So this is kind of something we talked about last week, which is waiting for a couple blocks to occur before we can really confirm that it's the true chain and not a forked chain. So that's reaching that level of finality. So again, just to run through this again, because it's one of the key concepts for today. First, we build the transaction, which is figuring out the data, who it's going to, who it's going from, the value, what it's made of. Once we know that, we sign that transaction using our private key. That signed transaction now gets broadcasted out to this network where it will be verified. And when that verification occurs, we again move from this mempool or this kind of pool of data in this decentralized network. We move from that to a future block space, applying changes to the new block, which and then gets posted in the new state as a new block. Again, once that occurs, that block gets broadcasted. The block's validity gets confirmed, thus confirming the transaction has executed correctly in that block because it's now in a confirmed. That transaction is confirmed because it's in a confirmed block. Again, reaching this level of finality. Cool. And now we're going to move to some live demos.
Okay, so now we are going to actually connect to a live Ethereum node, right? And so there's two things we can do. We can read, we can have it, the node return back some information for us. So this would be like reading the contents of the blockchain. And then we can also write to the blockchain, which is when we send a transaction to modify the current state. So here we're going to request the most recent block number that the nodes know about. So we come over here and pull up the terminal. Right.
So this might look a little complicated, but in reality, we're just going to be using this terminal to access a node. This is just it might look super complicated, but basically we're just asking it to give us the number of the most recent block.
And here we can see that the block number is this particular number encoded in hexadecimal. And this block number probably has changed by now that the network has new information about new blocks. So probably if we make another one of these requests to the node, we'll get a different number. Right, and this number is just the number relative to the Genesis block, which is block number 0. So that many blocks has passed since the beginning of Ethereum's inception. And I have another one where we can query the balance of an account. Yeah, if we do this, we can see that this particular address right, has this much balance. In this case, it would be ether. Okay. If can we all see this? So if I do it again, this address has this much ether balance. So a lot of what's going on behind blockchain apps, or if you build a blockchain app yourself, is this kind of sending a message to the network and requesting data, or sending transactions to the network.
Good question. That's the balance of someone's specific account.
Yes.
How are you able to look at that? Isn't that a private source?
So in traditionally, right, we have like for a bank, right, you can't just see anyone's balance. But for a public blockchain network like this, everyone's balances are exposed.
So maybe not the name. You can't see the name, but you can see the account number.
You can see the address of the account.
Have you guys is this kind of just like an example saying you can see somebody's account in the case that you had like the tools to kind of find that web address? Like not you wouldn't necessarily be able to do that.
Yeah, so when you have that address, you're able to query and see the balance of that address. There's also websites out there where you'll see just updated information of an addresses an address just received this much or just sent this much. It's all public.
Okay. And then for this one, we'll open up this tool and let's see.
So again, this looks complicated, but we'll show you guys what the core information that we're trying to show you here. But really, it is just a website that you can go to, and if you have the proper information, you're able to see all this stuff about a transaction that occurred.
Right, and in this case, we're actually requesting information about a block. And the particular block we are looking at is actually Ethereum's Genesis block, so block number 0. This is what it looks like. It's just a bunch of data.
Jonas, can you make it bigger?
Can I make it bigger? Yeah. And within this data contains all of the information about all the transactions that have happened in the block. Right, and then what else do we have? All right, so that was the Genesis block. We can also use a user wallet to send funds. So if you know about MetaMask, you can just pull this up and send to any address that we want. And right in the background, what it's doing is it's connecting to a node. And then once you send a transaction to the node, it propagates the transaction to the network. And eventually it'll get included in the block and all the wonderful things, right? So now we'll just look at a few key parts of a transaction. So we have our who to who, which address to which address, right? And each address is really derived from the public key, which is derived from the private key. So all of these addresses have corresponding private keys. And yeah, pretty simple. How much to send, right? This is just a value, and In this case, we are sending Ethereum because we're looking at the Ethereum blockchain, but if this was the Bitcoin blockchain, we would be sending Bitcoin. If it was Dogecoin, we would be sending Dogecoin, right? So these are just, this is just the native currency of a blockchain, right? Digital signature, we talked about this before, right? And we can kind of feed this long string of bytes into a signature verification function. And what that'll output is the origin of the transaction. So who actually sent this transaction, right? And the key part is, although we only know the public address from running this signature verification function, there's actually very strong cryptography that guarantees that the corresponding private key has signed the transaction, which authorizes things like sending funds and running smart contract functions, right? Transaction fee information, you might have heard about like transaction fees being like very high or transaction fees being very low. We require transaction fees in open blockchain networks because if we do not have transaction fees, people can just spam transactions and overload the network because transactions are free in that case. Or they can trigger infinite loops in smart contracts. Right, smart contracts just kind of contain arbitrary logic. And if you write an infinite loop in that arbitrary logic and you make all the nodes compute the infinite loop, right? This would also overload the network. Additionally, transaction fees are also an incentive, right? So this was one of the key innovations of Bitcoin, which is that there is an incentive to mine the next block, right? And yeah, that's that. The account nonce, right? So every address in Ethereum has their own associated nonce, and every time this address sends a transaction, the nonce gets incremented by 1. And this just makes all of the transactions that the account sends to be all unique. And in particular, nonces serve to prevent replay attacks, which is when you send the same signed transaction over and over. So if you send, transaction number 1, and then someone else sees your transaction, they can just copy it and then send it over and over, right? And perhaps drain your account. And when we query information about a transaction, there's also some information about the block that the transaction is included in. And so here we see block number, which is something we saw in the live demo. And then the block hash, which contains, it's like a summary of all of the information in the block. So we take all the contents of the block and we feed it into a hash function. And we get this block hash. Speaking of blocks, structure of a block. Okay, never mind, not a structure of a block. But here we see something fairly important. This is a way of storing transactions on the blockchain. So if you look at, just imagine that 1, 2, 3, 4, 5, 6, 7, 8. These are all transactions, and we can combine the ID or hash of the transactions, right? Feed them through a hash function to get this hash, and then if these two are hashes, we can feed these two hashes into this one and so on. And eventually what we get is this root, and this root is posted in the block. And if we know the root, or if we know the block number and we know the root, and we know some path to a transaction, we can actually confirm that the transaction has happened, basically. And this is very important because we want to keep things decentralized and very transparent. And many of the major blockchain implementations use this particular way to verify transactions. But really, the important point is that we have the ability to verify all of the history in the blockchain. Right? And so we can see that we have this root, and it's part of the blockchain. We have some blocks, and these hash pointers are just the previous block's hash, right? I think we talked about this a little bit. So every block is intrinsically linked to the previous block, hence blockchain. And this is another way of viewing what transactions are really doing, right? So we go from one state to another state to another state, and the way the state transition happens is through transactions, right? Transactions apply a change to this state, and we continue updating this database. Right. Okay. And that's it.